In this section, we will see how we can identify potential confounders with the help of DAGs. Let's see some terms that are used with directed acyclic graphs. A backdoor path is any path from the exposure to the disease, or E to D, that has an arrow pointing into E. In the figure, the path EAD, EABD, ECAD, and ECABD are the backdoor paths. The backdoor paths indicate confounding and need to be blocked. However, if the backdoor path has a collider, then we do not adjust for the collider, as the collider has already blocked the backdoor path, and so we call that path closed. A collider is a variable on a path in which two arrowheads enter or collide. In the figure, A is a collider because two arrows from C and B collide in it. Remember here that a variable itself is not a collider, but the path on which it resides makes it a collider or a non-collider. For example, in the figure, A is a collider on the path ECABD, which is right here. However, A is not a collider of the path EAD, which is this path here. The blocked path is the path that has the collider in it. In this example, the path ECABD is blocked. A path that does not contain a collider is not blocked. In the figure, path EAD and EABD are unblocked paths. Take a look at this figure and decide whether there is a backdoor path or not, and also whether there is a collider and if there is confounding. Hit the pause button, and when you're ready, we will continue. So in this case, we do have a backdoor path that goes from E, C, A, B, and D. Is there a collider? Yes. A is a collider because there are two arrowheads going into it. Is there confounding? The answer is no, because this path is the only path, which is ECABD, and it is blocked by the collider. This means that we don't need to adjust for anything. Let's take a look at the process we follow to identify confounders with DAGs. And these are potential confounders. We then can put them into the models and actually assess them statistically. So we first draw a DAG. How do we draw a DAG? Well, that's based on our knowledge of how the pathways are, and medical knowledge, literature review, and discussing with other experts. Once we've drawn the DAG, we remove all of the arrows going out of the exposure. The remaining path between the exposure and the disease are associations due to confounding. So we need to control for at least one variable on every path. Every time you control for a variable, you need to reassess, because you might have actually opened paths that were closed before. Now, if a path contains a collider, that path is blocked, and so you do not need to control for that. You don't need to control for any variable in that path. And again, if you are controlling for a collider, you will open that path. So you don't want to, at the end, include that variable in a model, because if you accidentally insert a collider in your statistical model, you might actually end up with more bias than you started with. So let's take a look at an example. So here we have the exposure is periodontal disease or gum disease, and the outcome is cardiovascular disease, and there are many studies that are investigating this association. However, smoking can be a confounder of this association. This is what we hypothesize, so we draw this DAG. This is one of the simplest DAGs. The first step we want to do is removing the arrow, the yellow arrow from E to D. So we want to cancel this arrow. Then we look at what path is left, where the ECD path is left. Is this path open or closed? This path is open because C is not a collider. So we concluded that C is a confounder. And therefore, we will need to include smoking and adjust for it in our modeling. Let's take a look at this example. First, we want to remove the arrow going from E to D, so that we ignore that. There is only one path left. It's E, U, C, and D. Now, do we have a collider in this path? Yes, C is a collider because there are two arrows going into it. So this path is blocked, and we do not need to control for any of these variables. We can say that the association between the exposure and the disease is unconfounded, and we can use an adjusted odds ratio. And this can be confirmed when we do modeling. Here is another example. Let's remove the arrow going out of the E, so that's this one here. There is only one path left, which is ECUD. We do not see any colliders, so this path is open, and we do need to control for at least one variable on this path. We forgot to measure U, but we can control for C. And if we control for C, then we are okay. So we do not need to worry that we forgot to measure this variable. So the association between this exposure and disease is confounded by C, and we will need, in our model, we will need to assess this, and if this is correct, we will need to adjust for C. So here is a mini DAG that I saw once in an NIH grant application. And so this was for a case control study where you first identify the cases and the controls, and then you ask them about some exposure. So the arrow in this case was pointing from D to E, and you never want to do that. So the arrow always should go from E to D.